Hi, this video is the part 2 of this problem 235, lowest common ancestor of a binary search tree. So I'm not going to go through the problem and read the problem. You can watch the video for this problem for part 1. So let's recap what we have done in part 1. So for this problem, this is the algorithm and we are using the recursive approach to solve this problem. So in step 1, this is the step 1. Step 1 is the recursive base case. We need to define the base case to prevent the stack overflow. So we check if the root is null and if the root value is equal to the given value in P, or if the root is equal to Q, then in that case we just simply return root, because that is the base case. So next step. Step 2 is the decomposition part of the recursive algorithm. So in here we check for the P and Q value in the left subtree and right subtree. That's what we are doing in here. Let left is equal to lowest common ancestor. So we are calling the function itself. In here we are passing in the root. We are passing in root.left because we want to check for the left side of the subtree, and we pass in P and Q value. Same thing in here. We check for the right and right subtree. We call the function itself and we will pass in root.right, and we pass the P and Q value. So this is the composition part, that step. In here we are check if the left is null, the left subtree is null, then we will return right and we will continue to check in the right subtree. Else if right is null, if the right is null, then we will return left and we will continue to check in the left subtree. Otherwise, then we will return the root. So let's go through the algorithm step by step, and then we can discuss the time and space complexity again. So I have drawn here the recursive call stack. This is the call stack, and then in here, just to visualize this algorithm, the code walkthrough clearer, I have written the root and the explanation. So let's start with the first call. The first call is lowest common ancestor. So we are using this function, and in the root we are passing in the root itself, which is 6, and P and Q it is 5 and 8. This is what we're looking for, 5 and 8. Okay, so this is the first call. Next step. So now we check root is not. So in this step we check 6 is not null, 6 is not equal to 5, 6 is not equal to 8. So we check for the left side. So it will come to here. So left, we call the function itself root.left. So 6 root.left is 2. So we are passing in 2. So we are checking for this left subtree. So in here we check 2 is not null. Again we check 2 is not 5, 2 is not equal to 8. So we will make so it is not. So we will make that further call again. So in this case, in this step we are up to here, so 0. So 2 is currently the root, and root.left becomes 0. So we check 0 is not null, 0 is not 5, 0 is not 8. So we are back to here. It is not none of that, so we come to here again. It will call into here, so we go for root.left. In here we check. Now this root is the leaf node. There is no more father-child node, so it will be left node will be null, right node is also null. So in here we are checking for the left, so it is null. Root it's not. Oh no, sorry. It should be root is equal to null. So null is equal to null. So in here we have reached one of the base case. This is the base case. So my apology. It should be equal to. So in this case, then we are going to return the root. So because root is equal to null, then we will return the root. So that is the base case. So now we are returning the root. So this now this left call will be pop up from the call stack, and then we will return the root. After we return the root, we will check for the next, this part will get executed, so we will check for the right side. root.right. So now it's null. Sorry again, null is equal to null, so it should be equal. So in this case, we have reached one of the base case, so we will return the root, which is 0. So we have checked all the left subtree on here. So we will get back to 0, and then from 0 we will go back to 2. So 0 will be out of the call stack. This will be pop up from the call stack, and we will go back to here. So from here, the next part is we have to check for the right side. So we are executing this one. So root.right value is 4. So we check 4 is not equal to null, 4 is not equal to 5, 4 is not equal to 8. So we make the further subcall. So 4.left, so this is the root.left is 3, so we are checking for the 3. So again, it is not equal. So this doesn't meet the requirement, so we will come back to here, left. So we check for the 3, which is the current root, and then root.left, which will be null. So root.left, which is null, sorry again, my typing error, null is equal to null. That is one of the base case. So in this case, we are going to return the root, which is 3. So that will be this will be pop out from the recursive call stack, and then after that we will check for the right side. We check for the right side, it is null, sorry again, null is equal to null, so that is one of the base case. So we are going to call that back to return it back to 4. So 3 will be pop out from the recursive call stack. So now we are at 4. So we have checked for the left subtree. So we are now in this subtree. So we will check for the right. Root.right. So when we check for the root.right, we can see that this is P value. P is equal to 5. In here we found the note 5 is equal to 5. So in this case, then left subtree is now we found for the right, so we are going to return it back. So when we return, we are going to pop out that to pop this out from the call stack, pop this out from the call stack. Eventually we will come back to 2. So we on this left tree we have checked for everything, and we found P. So from here we found P, so we will root.left. So that will also get popped out from the call stack. So now we are back to root, which is 6. So after 6, then we would have to check for the right side. When we check on the right side, root.right, the value is 8. So in here we can see that 8 is Q is 8, 8 is equal to 8. So in here we see the right subtree is 8, but they of course they will not be in the call stack, but I have written it here to clearly understand, to have a clearer understanding. So now we know. So as per our algorithm, we have found for the left is not null, right is not null, because left is 8 and left is 5, right is 8. So we just simply return the root. Now it is 6. So this is how this algorithm, this is how the recursive call stack work, and I strongly encourage you to do that by hand, and that will help you have a better understanding of the recursive call stack for this algorithm, or any tree problem if you are using the recursion approach. So let's discuss the time and space complexity. As you see in this in the tree that we have searched, it is the average case. So in here the recursive call stack will be log of n, but there will be a case of there could potentially be a skew tree, and so for example, let's say we will have a 6 at the beginning, and then P and Q value they are far right skew here. So in that case, then recursive call stack will be quite deep. So in that case, it will be worst case will be O of n. So in terms of space complexity, it will be O of n, because we will use the space complexity. We always think about the worst case, so it will be O of n. Okay, so this is one approach. And I want to bring this diagram up again to remind you the difference between the binary tree and the binary search tree. Binary search tree is not order, as you can see in here. 6, as you can see in here, 5 is greater than 2, and this example is better. 8 is greater than 6 and also greater than 2, but it is on this side. So binary tree, it is not order, but binary search tree is order. So as you can see in here, all the child value on the left side of the root, it is less than the root itself. All the child value on the right side of the root is greater than the root itself. So that is the properties of the binary search tree. The algorithm that I went through in here, this algorithm, it will work for both binary tree and binary search tree, because we are checking for every single left subtree and every single right subtree. So we can optimize that or do that, solve this problem slightly differently. But in this algorithm, we are using the binary search property. So in the binary search property, we know that the value of P, the value, left child value, if we compare to the root, will always be less, and if we right child value, if we compare to the right, will always be greater. So we can take advantage of this property, and we can check and cut down the traversal time. So so in here, in this if clause, we are checking only for the left subtree. So we check if the p value is less than the root of the value given at the root, and also q if it is less than the root value. If they are both are less than the root value, then we only have to check for the left subtree. So that's what we are doing. We call the function itself in here lowest common ancestor, and we pass in root.left. We are only checking for the left side. Again, in here, for this one, we are checking for the right side. If the p value and q value, if they are greater than the root value, then we are only checking for the right side of the subtree. So in that way, we can cut down some of the unnecessary steps. Otherwise, then we find that, so we will return the root. So with this approach, it will work for only binary search tree. This algorithm will not work for binary tree. So there is another Leetcode problem, exactly the same, but in here, instead of the binary search tree, the property is only binary tree. So if you use this algorithm in here, because it does not have that property, so this algorithm will not work. But the algorithm that I have shown step through in detail, this algorithm, it will work for both binary tree and binary search tree. So let's summarize. In this video, for this particular problem, we learned the difference between binary tree and binary search tree, and why binary tree is a recursive data structure. Since binary search tree is a variant of the binary tree, we can use the recursive algorithm to solve this problem. And we also learned the general recursive approach, general recursive algorithm, and break it down into steps. And we learned two algorithm. One is only for the binary search tree. We take advantage of the binary search tree and you solve this recursively, or we can also solve this problem using the using this approach, using the general recursive approach. So thanks for watching. Please make sure to subscribe and press the like button if you find this video helpful. Join our Wednesday weekly data structure and algorithm night, where we organize peer-to-peer coding interview. Thank you.